Okay, so as I mentioned, this month is grading month. This past week was still bad, but I'm going to get to the grading. All right. Obviously, by the withdrawal deadline, obviously. All right. Okay. So anyway, today is today is Tuesday. Right? Today is Tuesday, October 6th. We're going to start basic right triangle trig, Sokatoa, sine, cosine, and tangent. I have some great videos for you today, by the way. We'll have some time for homework questions at the end and beyond. And we'll have more great time for questions next time. All day session on Thursday. All right. So that's where we are at. And the homework will be due this Friday after the homework session, right? Okay, homework session is Thursday, October 8th. Homework is due Friday, October 9th by midnight, 11:59 p.m. basically, right? Okay, that's when the homework is due for chapters 2 and 3. Chapters 2 and 3. No trig will be due this week. I encourage you to keep up, but no trig will be due this week. All right. So any questions before we move on from the schedule? Any questions? All right. Okay, so we have some great videos and stuff for you. And right off the bat, I have some good ones. Basic trig functions. I hope you know are basic trig functions. 6 basic trig functions. I hope you know them well from Math 104. All right. Now, these were sections 4.2, 4.3, and 4.4 in the old Larson textbooks. I just sort of blended all those sections together. We're going to talk about trig functions, their values, and related identities. So a lot to do in these 3 bulk sections. All right, so we're going to consider 2 general approaches to these basic trig functions. The right triangle approach, which is really great for your basic quadrant 1 angles, and the unit circle approach, which is a good general approach and also really essential for the quadrantal angles, things like 0, pi/2 radians, pi radians, and so forth. Things like the perpendicular lines and straight lines, the kinds of angles you get from those. Okay, now the right triangle approach. Here is the setup. So let's say that we care about this angle theta. And let's assume for now, for the time being, that theta is acute. So we're going to focus on acute angles for right now. And we'll extend these ideas later on. Observe that the 2 acute angles of a right triangle are complementary. These add up to 90 degrees. We have 180 degrees total in the triangle, 90 degrees taken up by the right angle over here in this right triangle, and the remaining 90 degrees will be split up between these 2 complementary angles. We're going to look at one of these. And make sure that you clearly indicate which angle you're talking about. I want to know that you're talking about this angle, for example, as opposed to this one. Okay, so relative to this angle, labeled theta, this here is the opposite side. It's the side that this angle faces. It's the opposing side. The angle itself consists of these 2 line segments. It consists of these 2 line segments connected at this common point. The adjacent side is one of the legs of the right triangle. The 2 legs are perpendicular to each other on the right triangle. The hypotenuse is the longest side of the right triangle. So relative to this angle theta, we can identify an opposite side and an adjacent side. Regardless of which angle you're talking about, the hypotenuse will always be the longest side, and it's always going to face the right angle. Only right triangles will have hypotenuse. The hypotenuse always faces the right angle, and it is always the longest side. The hypotenuse will always be longer than each of these 2 legs. And by the way, when I refer to a leg or a hypotenuse, or a side in general, I may be referring to the actual geometric figure or to the length of that figure. So understand the context. So once again, the other 2 sides are the legs, The opposite side faces the angle. The adjacent side sort of makes up the angle, together with the hypotenuse. Remember, we're not focusing on this right angle here. We're focusing on one of these two acute angles that are complementary. Okay. Now, let's talk about the ancient curse, Sokatoa. Many of you have seen this, many others haven't, but it's really convenient to know this. It's a nice, convenient way of remembering how to develop these ratios for the sine, the cosine, and the tangent of this angle theta. And again, sine, cosine, and tangent are going to correspond to ratios of these side lengths. And we're going to use ratios of side lengths to define these 6 basic trig functions, at least in the case where theta is acute. We'll generalize it later on. Sokatoa. What does that stand for? All right. So the sine of theta, again, it's nice to put parentheses. The sine of theta is the length of the opposite side over the length of the hypotenuse. I'll put that in, let's see, blue here. Right. So the sine of theta is given by basically opposite over hypotenuse. Opposite over hypotenuse. It's the ratio of these side lengths. And observe that this value can never be greater than 1 because the hypotenuse will always be the longest side of the right triangle. In particular, it will be always longer than the opposite side. So notice this will never be greater than 1. And for an acute angle, it will be somewhere strictly between 0 and 1. Okay, now what about cosine of theta? I'll erase these marks over here. Cosine of theta. The cosine of theta, ca, is given by adjacent over hypotenuse. So remember was, okay, so was telling us that sine of theta was opposite over hypotenuse. Ca is now telling us that cosine of theta is adjacent over hypotenuse. The adjacent side over the hypotenuse. The ratio of these lengths. Again, it's not going to be any greater than 1, and for an acute angle, it'll be strictly between 0 and 1. It goes Sohcahtoa. If you say toe, then you might not know if it's T-O-H or T-O-A. So I like to say toa. Sokatoa. Tangent of theta is given by opposite over adjacent. Opposite over adjacent. Now bear in mind, unlike sine and cosine, this ratio could be greater than 1. It's quite possible that the opposite side is longer than the adjacent side. So tangent of theta is going to have a different range. In fact, in the end, it will have all real numbers as its range for various values of theta. All right, so we can use this ancient curse, Sohcahtoa, to describe how we can define the sine, the cosine, and the tangent of theta as ratios of side lengths. Sohcahtoa. So, sine is opposite over hypotenuse. Ca, cosine is adjacent over hypotenuse. Toa, tangent of theta is opposite over adjacent. So these are our 3 basic trig functions in terms of theta. We're going to look at their 3 partner reciprocal functions in the next video.
Any questions thus far? Any questions thus far? All right, let's go on to the reciprocals.
Hi everyone, we're back to right triangle trig. We ended last time with the ancient curse, Sokatoa, which reminded us that sine of theta was opposite over hypotenuse, cosine of theta was adjacent over hypotenuse, and tangent of theta was opposite over adjacent. Where this is theta, this is the opposite side, this is the adjacent side, and this longest side is hypotenuse. Now try to remember from your trig class, what was the reciprocal of sine of theta? We're going to get the 3 reciprocal functions for these, and we're going to get the reciprocal identities. the first of 5 groups of identities we'll discuss in chapter 4. What's the reciprocal of sine of theta? What is 1 over sine of theta? Many of you may have said secant of theta, and you'll be wrong. The reciprocal of sine of theta is cosecant of theta, and a lot of people forget that. The reciprocal identities. This is how we'll define these 3 additional trig functions. Cosecant of theta, again, parentheses are nice. Cosecant of theta is the reciprocal of sine of theta. Secant of theta is the reciprocal of cosine of theta. And cotangent of theta, conveniently, is the reciprocal of tangent of theta. But remember, the reciprocal of sine of theta is not secant of theta, it's cosecant of theta. Do not mix these up. It's kind of like when we had horizontal translations, where we were doing minus versus plus, shifting right versus left. It's the opposite from what you expect. You might think the reciprocal of sine of theta is secant of theta, but you'd be wrong. It's cosecant of theta. That's reciprocal of sine of theta. As it turns out, this will help us with the Pythagorean identities later on. So it's helpful to remember that the cosecant of theta is the reciprocal of sine of theta. The secant of theta, on the other hand, is the reciprocal of cosine of theta. And as expected, the cotangent of theta is the reciprocal of tangent of theta. I think it's helpful to think of these in terms of reciprocals. I don't think that cho, sha, cow will help us so much, as Sokatoa did. Oh, one other thing. If theta is quadrantal, like 0, pi over 2, pi, and so forth, then it's possible that sine, cosine, or tangent could be 0. In which case, these could be undefined. In fact, tangent itself could be undefined. Now, here's something that's kind of weird. In basic trig, we can think of 0 and undefined as reciprocals of each other. Now, again, this will not happen if theta is acute, but this can happen if theta is quadrantal, like 0, pi over 2, pi, or so forth. So, for example, if sine of theta is 0, then cosecant of theta will be undefined. So your algebra teacher would agree that the reciprocal of 0 is undefined. There's no problem there. But here's something that might sound weird to your algebra teacher. Let's say the tangent of theta is undefined. Then for that value of theta, cotangent of theta will be 0. So when it comes to basic trig, you can informally say that in basic examples, the reciprocal of undefined is 0. Now, you can't say that formally, and your algebra teacher would freak out. So don't tell your algebra teacher that the reciprocal of undefined is 0. That's not a proper thing to say. But for all practical purposes, hey, if tangent of theta, say, is undefined, then yes, cotangent of theta will be 0. So we can treat 0 and undefined as reciprocals informally in basic trig. All right. Now, in addition to the reciprocal identities, the second group of identities we'll look at will be the quotient identities. We have 2 of these. Tangent of theta is sine of theta over cosine of theta. It's the quotient of these 2 basic trig functions of theta. Cotangent of theta is the reciprocal, so you just flip this fraction. Cotangent of theta is going to be, you flip these guys, cosine of theta over sine of theta. So it's helpful to remember tangent of theta is sine of theta over cosine of theta. For cotangent of theta, you take the reciprocal. Now, why is this consistent with Sohcahtoa? So here's some very informal algebra. So let's assume theta is acute for now. Sine of theta, so, is opposite over hypotenuse. Cosine of theta, ca, is adjacent over hypotenuse. Now, if you take this compound fraction, and if you multiply by hypotenuse over hypotenuse, on top and bottom, you basically cancel out hypotenuses. The 2 little bottoms disappear. They cancel out. And we end up with opposite over adjacent, which was tangent of theta. That's TOA. Tangent of theta is opposite over adjacent. So the quotient identity here is reciprocal with Sokatoa. You can do something similar with cotangent of theta and its identity. So the reciprocal identities and the quotient identities make up our first two blocks of trig identities. Our third block will be the cofunction identities, which we'll discuss soon enough. And then later on, we'll have the Pythagorean and even odd identities. Speaking of Pythagorean, let's talk about the Pythagorean Theorem, which will be the foundation for the Pythagorean identities. All right, this should look familiar. The Pythagorean Theorem. There are literally hundreds of proofs for the Pythagorean Theorem. Actually, we don't think that Pythagoras himself, the ancient Greek mathematician, devised one for himself. He basically stole other people's credit for this, the Pythagorean Theorem. Now, actually, President James Garfield came up with a proof. That's not why they shot him, but he did come up with a proof. He was a very smart man. He was not shot by a jealous mathematician. All right, the Pythagorean Theorem. So let's say that the opposite side is A in length, the adjacent side is B in length, the hypotenuse is C in length. This should look familiar. A squared plus B squared equals C squared, the Pythagorean Theorem. The square of the hypotenuse equals the sum of the squares of the other two sides. This is famously misstated in The Wizard of Oz and The Simpsons. Okay. Now, when you apply the Pythagorean Theorem, it's helpful to remember the Pythagorean triples. In fact, if you know these Pythagorean triples, you won't have to crank through this. The Pythagorean triples are a set of three integers that can represent the side lengths of a right triangle. The most famous one looks like this. So let's say that the units are in meters, let's say, some common unit. Let's say that this side length is 3 meters. I'll put the unit, 3 meters. Let's say this side length is 4 meters. Notice these are the two legs of a right triangle. If the two legs of a right triangle have lengths 3 meters and 4 meters, we know that the length of the hypotenuse, or just the hypotenuse, is going to be 5 meters, because we know this Pythagorean triple, 3, 4, 5. That's because 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. In fact, proofs often involve physical squares. The area of this square plus the area of this square equals the area of this square. 9 plus 16 equals 25. The sum of the squares of the two legs equals the square of the hypotenuse. Now, let's say that, now before we go on, I want to point something out. I'll go ahead and erase these. Again, the actual squares are often used in proofs. What if instead we had this? What if we had the 4 meters? What if we had the 4 meters on the hypotenuse? Does that mean that this side length here is going to be 5 meters? Do we automatically put 5 meters on the missing side? And the answer is no. Why not? The hypotenuse is supposed to be what? What side? The longest side of the right triangle. So there's no way that you can have a triangle like this where 4 meters is the hypotenuse and yet 5 meters is a longer leg. This cannot happen. So if you apply this 3, 4, 5 Pythagorean triple, make sure, not just that you're dealing with a common unit, but make sure that the longest side length is in fact the hypotenuse, not a leg. If you have a situation like this, then sorry, but you're pretty much going to have to crank through this equation. Okay, now there are other famous Pythagorean triples besides 3, 4, 5. We have 5, 12, 13. If this is 5 meters, and if this is 12 meters, then this is 13 meters on the hypotenuse. And that's because 25, the square, plus 144 equals 169. Also, the third famous Pythagorean triple is 8, 5, 17. If 8 is here and 15 is here, then this has to be 17. And that's because 64 plus 225 is 289. Now, in fact, number theory tells us that there are infinitely many of these primitive Pythagorean triples. I say primitive because you can get multiples of these, right? Instead of 3, 4, 5, you could have 6, 8, 10, or 9, 12, 15, or for that matter, 30, 40, 50, or 300, 400, 500. So there are infinitely many Pythagorean triples just by considering multiples of these. But even if you disregard those multiple situations, there are infinitely many primitive Pythagorean triples where there are no common factors besides plus or minus 1. Now, these are the 3 most famous Pythagorean triples. There are less famous ones. 7, 4, 25.
24.
9, 40, 41. Those are probably the next 2 nice ones. Again, there are infinitely many primitive Pythagorean triples. We have 3 that are really nice. And on the SATs, they'd expect you to remember these. These are 2 pretty nice ones, but you wouldn't be expected to remember these. And again, there are infinitely many other primitive Pythagorean triples. And you can always make more by taking multiples, like 6, 8, 10, or 30, 40, 50, and so forth. Again, warning, remember the hypotenuse must be the longest side. So the missing number is not just the missing side. Okay, don't just do that. The hypotenuse must be the longest side. What I mentioned before, with 3, 4, 5, 6, 8, 10, and 9, 12, 15, and 30, 40, 50, these are examples of similar triangles. Triangles that have the same shape, but maybe not the same size. Okay, so for example, if this is a 3, 4, 5, then maybe this is a 6, 8, 10, same shape but different size, and so forth. They're like nested triangles. Now, one nice thing about these similar triangles is that their corresponding side lengths are in the same proportion, and they have the same angles. And these angles will have the same sine value, cosine value, and so forth. Okay, so if you know these primitive Pythagorean triples and their multiples, the fact that multiples will work, if you know these primitive Pythagorean triples and their multiples, then that helps you work out the missing sides for these right triangles. Otherwise, you pretty much have to crank through this. Again, if the 3 were here and the 4 were here, you'd have to work through this thing. Finally, in our next video, we're going to get an example where we will apply the Pythagorean theorem and we'll revisit Sokatoa and the reciprocal identities and the quotient identities. Until then.
All right, now, okay, so that's all great, but I'm going to show you some really great videos. All right.
Hi, everyone. Let's do an example of this right triangle trig. Okay, let's say that theta is an acute angle such that cosine of theta is 4/7. Find all 6 basic trig values for theta. So I'm giving you one of them. Find the other 5 and remind us of this. Okay, we have enough information. We can find sine of theta and all of the other buddies. Now, first of all, it's helpful to sketch a right triangle model. You don't need a ruler to do this, but make sure that longer side lengths do in fact lead to longer sides when you draw these things. In particular, the hypotenuse must be the longest side. So let's sketch a right triangle model. Let's say that we have this right triangle. It's good to indicate the right angle with a square. Here's our angle theta, one of the 2 acute angles. Let's take this angle theta. And we're given that cosine of theta is 4/7. Now remember, cosine of theta is adjacent. I'm going to type this. Remember that cosine of theta is adjacent over hypotenuse. Cosine of theta is adjacent over hypotenuse. Now, instead, you could have done this. Cosine of theta is 4/7 over 1. This would work, but I would think that we would want to avoid fractions right now, so this might make things a bit easier. Okay, it turns out that the missing side length will be root 33. If we want, we could assume these are all in meters. Let's assume a common unit. Okay, so we can assume that these are all in meters. It turns out this will be root 33. How do we know that? How can we find this out? From whose theorem? Mr. Pythagoras. Again, it wasn't his theorem, really, but it was named after him. The Pythagorean Theorem. Okay, bear in mind, we don't have a Pythagorean triple here. It's not a 3, 4, 5 situation. If that were a 5, then we'd have a 3 here, right? The Pythagorean Theorem. X, the unknown right now, x squared plus 4 squared equals 7 squared. Now, a lot of students are tempted to do x squared equals 4 squared plus 7 squared. They love to isolate x squared on one side. But here, sorry folks, but the x squared is buried in there. If you try to isolate x squared right now, you'll probably get it wrong. Okay, so what are these squares? We have x squared plus the square of 4 is 16 equals the square of 7 is 49. We're solving for x squared and then x. What do we do with the 16? We subtract it from both sides. Don't say move, say subtract. We subtract 16 from both sides. X squared equals 49 minus 16 is 33. And then we apply the square root method. If x squared is 33, then technically x can be plus or minus the square root of 33. But since theta is an acute angle, we're going to use the positive number for this. Now you might be saying, well, hey, aren't lengths always positive? Well, yes, but it turns out that if we move to other quadrants, we sometimes use signed lengths. We sometimes put the negative number. For example, if this were a triangle in quadrant 3 or quadrant 4, we'd put a negative root 3, a negative root 33 down here or down here to label the side. But since theta is acute, we always take the positive number for our indicated length, our indicated signed length. Okay, so we take x equals root 33, which is simplified. Again, if we have 4 meters here and 7 meters here, this would also be in meters. For right now, I'm not worried about units. Okay, so we know now that this missing side length is root 33, meters or whatever. Well, that really unlocks the whole puzzle for us. If we know this missing side length, then we can get all the ratios we need. All right, so let's do it. In fact, it might be a good idea if I take a copy. Yeah, so let's keep this up here. Let me keep this up here, and I'll use my copy of this file. Well, here we go. Here we go. All right. Now remember, we were given, right off the bat, we were given that cosine of theta was 4/7. Okay, we were given this. But now we can figure out the other 5 ratios. What about sine of theta? Sine of theta, remember Sokatoa. Sine of theta is opposite over hypotenuse. Relative to theta, opposite is root 33. In fact, I may as well say this is opposite. And this is adjacent, the 4. That's going to be adjacent. Let's type it in. That's adjacent over there. Opposite over here. And the 7 here, remember, is the hypotenuse. Relative to theta, here's the cast of characters. This is the hypotenuse regardless. Okay, here we go. Sine of theta is opposite over hypotenuse. It's root 33 over 7, and that's simplified. You may notice this is less than 1. Root 36 is less than 6. Cosine of theta is 4/7. We made it so. Tangent of theta, Sohcahtoa. Tangent of theta is toa, opposite over adjacent. Opposite is root 33, adjacent is 4. Tangent of theta is root 33 over 4, and that's simplified. Okay, now from these, we can get the 3 reciprocal values. The reciprocal of sine of theta is what? Not secant of theta, it's cosecant of theta. the reciprocal of sine of theta is cosecant of theta. We flip this fraction. We get 7 over root 33. But what's our problem with this? We can rationalize the denominator. We multiply by 1 in the form of root 33 over root 33. We multiply fractions across. 7 times root 33 is 7 root 33. On the bottom, root 33 times root 33 is 33. And you see here that this is simplified. 7 and 33, we can't do any reduction there. This is cosecant of theta in nicest, simplest form. Remember that if we have the square root of an integer down in the bottom, a non-zero integer, then we tend to rationalize the denominator. In fact, let's say that that's typically required for these trig problems. When would we not rationalize? If we have, for example, 1 over the square root of x, well, x itself could be an irrational number like pi or something. So we tend not to rationalize the denominator in a situation like this, where we have a variable or potentially irrational radicand. But here, 33 is an integer. We tend to rationalize. This is easy. The cosine of theta is 4/7. Therefore, its reciprocal, the what? The secant of theta is, flip this, 7/4. Remember, cosine of theta cannot be greater than 1. This is 4/7. But secant of theta, in fact, will tend to be greater than 1. Here, it's 7/4. If cosine of theta is less than 1, secant of theta will be greater than 1. No surprise there. Now for tangent of theta, we have root 33 over 4. So it's reciprocal, the cotangent of theta. We start by flipping the fraction. It's 4 over root 33, but we have an integer inside there, down there. So we rationalize the denominator, multiply by, again, root 33 over root 33. Remember that whole thing there is 1, right? This whole fraction here is 1, so that's legal. We multiply these and we get 4 root 33 over 33. That's the cotangent of theta. So in blue, I'm going to circle our final answers. Sine of theta is root 33 over 7. Cosine of theta, that was given, 4/7. We made it so. Tangent of theta is root 33 over 4. The reciprocals here, cosecant of theta is 7 root 33 over 33. Secant of theta is 7/4. Nice rational number. Cotangent of theta is 4 root 33 over 33. And voila, we have our 6 basic trig values for this acute angle theta.
Oh, and by the way, made it so. Yes, that was a Star Trek Picard reference. Yes, it was.
If theta were not acute, it's possible some of these might be negative. All right. So now, in our next video, we're going to look at the sine, cosine, and so forth for special angles, like 30 degrees, 60 degrees, and so forth. And where do those values come from? The sine of 30 degrees, where did that come from? We'll see the answer in the next video.
Right, any questions so far? Questions so far?
Hi, everyone. We're continuing with our journey through right triangle trigonometry. Now, you might be wondering how we get the basic trig values for things like 30 degrees, 45 degrees, and 60 degrees. For example, how would we find the sine of 45 degrees? Well, it turns out that we're going to use 2 families of similar triangles. These are special triangles. One family is the 45, 45, 90-degree family of similar triangles. Again, similar triangles have the same shape, but maybe different sizes. Now, these 45, 45, 90-degree triangles are sometimes known as isosceles right triangles. Take a look here. We have here a 45, 45, 90-degree right triangle. These are, by definition, isosceles, meaning that the 2 legs have the same length. They're congruent. Of course, the hypotenuse is still the longest side. Now, it makes sense that in a triangle, equal or congruent angles will face equal or congruent sides. Now, the most basic 45-45 90-degree triangle, the basic triangle we like to base everything on, is this one over here, where each leg length is 1 unit, say 1 meter. By the Pythagorean theorem, we then get that the length of the hypotenuse is the square root of 2. By the way, the fact that the square root of 2 is an irrational number here, this hypotenuse is irrational, that really freaked out the ancient Pythagoreans. In fact that this was an irrational number so freaked them out that there are legends that Pythagoras would have people who released this secret taken out, literally taken out. They'd be thrown off of boats with an anchor. Or there was a rumor that Pythagoras himself stabbed someone who revealed the secret, that the square root of 2, this hypotenuse, was irrational. So I hope that you as students appreciate this knowledge that you're getting, because people have died for it. Okay, anyway, so here we have 1 meter, 1 meter. This is the square root of 2 meters, irrational. All right, now, given these side lengths, hey, we can come up with the sine of 45 degrees and so forth. So what is the sine of 45 degrees? Well, Sokatoa, sine is opposite over hypotenuse. It's 1 over root 2. Pulling this up over here. The sine of 45 degrees, also the cosine of 45 degrees. Cosine is adjacent over hypotenuse. That's also 1 over root 2. We rationalize the denominator and we get root 2 over 2. So both sine of 45 degrees and cosine of 45 degrees, again, it's good to put parentheses, they both have as their value root 2 over 2. Now from these, we can also get the reciprocal values, the cosecant of 45 degrees and the secant of 45 degrees. Now it's true that if you turn this guy upside down, 2 divided by the square root of 2 is in fact root 2. If you don't believe me, multiply by root 2 on both sides, and we see that 2 equals root 2 times root 2. That's a true statement. So we could do it that way. We could turn this upside down. 2 over root 2 is root 2, but wait a minute. Look at this guy. One advantage to the unrationalized version of these trig values is that if you take this guy and turn him upside down, hey, you get root 2 over 1. So these unrationalized versions of these trig values can be useful, especially when you're taking reciprocals. The reciprocal of this is clearly root 2. So this is the cosecant and the secant of 45 degrees. Now what about the tangent of 45 degrees? Sohcahtoa, tangent of 45 degrees is opposite over adjacent. 1 over 1 is 1. And its reciprocal, cotangent of 45 degrees, is also 1. So fairly quickly, we're able to get all 6 basic trig values for 45 degrees by using the properties of the 45, 45, 90-degree triangle you see here. Again, it's a whole family of similar triangles, but this is the nicest, easiest one to work with. 1, 1, root 2. Okay. Now bear in mind for similar triangles, if this is 10 meters, for example, if that's 10 meters, then that's 10 root 2 meters. So you have similar, in fact, you have the same trig values even if you blow up or shrink this triangle. Because remember, these trig values correspond to ratios of sides on this right triangle. So even if we multiply everything by 10 meters, the ratios between pairs of sides will still be the same. For example, the sine of 45 degrees will always be 1 over root 2, or root 2 over 2, even if this is 10 meters and this is 10 root 2 meters. All right. So what about 30 degrees and 60 degrees? Well, we're going to look at this second family of similar right triangles, a second family of important, special, similar right triangles, 30, 60, 90-degree triangles. Now, it turns out that in order to analyze these, it's easy to begin with an equilateral triangle, a triangle in which all 3 sides are congruent, they have equal lengths, and all 3 interior angles are 60 degrees. So we're going to start with this equilateral triangle over here. Let's say this is 2 meters, 2 meters, 2 meters. So this big triangle here is an equilateral triangle with common side length 2 meters. 2 meters turns out to be convenient because we're going to split this side in half so that this is just 1 meter. Okay, so we start with this equilateral triangle of side length 2 meters, and we're going to drop this perpendicular, which is a common trick in right triangle trig. We drop a perpendicular, we have a right angle over here, and the 60-degree angle over here is bisected into 30 degrees and 30 degrees. Now, what we have now is a situation where we have 2 congruent right triangles. Let's look at the one in red here. We have here a 30, 60, 90-degree right triangle. 30 degrees here, 60 degrees here. Because it's a different angle measure, I'll use 2 arcs, and the right angle, 90 degrees over here. Okay, now remember, we bisected this side over here. We split it into 2 equal sized pieces. If the entire side length here is 2 meters from here to here, then it's just 1 meter from here to here. 1 meter over here. This side length is still 2 meters. The hypotenuse is still 2 meters. That was the original side length. So then, how do we get this root 3 meters? Well, it's from Mr. Pythagoras, the Pythagorean Theorem. From the Pythagorean Theorem, we get that the missing side length here is root 3 meters. Again, it's irrational, like the root 2 meters from before. So this is our favorite 30, 60, 90-degree right triangle. The one with side lengths 1, root 3, and 2, using the same unit. The hypotenuse of a 30, 60, 90-degree right triangle will always be twice as long as the shortest side, and the medium side will always be root 3 times as long as the shortest side. In a 30, 60, 90-degree right triangle, the shortest side faces the smallest angle, the 30-degree angle. The medium side length faces the medium angle, the 60-degree angle. And of course, the hypotenuse, the longest side, faces the largest angle, the 90-degree angle. In general, in a triangle, the shorter sides face the smaller angles, the longer sides face the larger angles. Now, from these side lengths, we can get ratios and get the sine of 30 degrees and so forth. So what is the sine of 30 degrees? What is the sine of 30 degrees? I'll use blue to make things clearer. What is the sine of 30 degrees? All right, the sine of 30 degrees, Sokatoa. Sine of 30 degrees will be opposite over hypotenuse. The opposite side length, 1 unit. The hypotenuse, 2 units. The sine of 30 degrees is 1 over 2. It's 1/2. The sine of 30 degrees is 1/2. Also, the cosine of 60 degrees. Let's shift our perspective. If we look at the 60-degree angle, the cosine of 60 degrees is given by adjacent over hypotenuse. The adjacent side has length 1 unit. The hypotenuse has length 2 units. Adjacent over hypotenuse is again 1/2. So both the sine of 30 degrees and the cosine of 60 degrees will be 1/2. And the fact that these two values are equal is no coincidence. That's going to take us to the cofunction identities. All right. Before I go on to that, I'll very quickly observe the sine of 60 degrees will be root 3 over 2. That's also the cosine of 30 degrees. But notice that we have that pattern, right? It seems like the sine of one angle here is the cosine of the other acute angle over here. The sine of 30 degrees equals the cosine of 60 degrees. Likewise, the sine of 60 degrees equals the cosine of 30 degrees. Now, why is that? Remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Let's take a look at this shortest side here with length 1 unit. It's the opposite side for 30 degrees and the adjacent side for 60 degrees. Whereas the root 3 here is the length of the opposite side for 60 degrees, yet it's the adjacent side for 30 degrees. So when we switch from one acute angle to the other angle, we're switching the adjacent and opposite sides. So it makes sense that the sine of 30 degrees is the cosine of 60 degrees, because the opposite for this angle is the adjacent for this angle. Oh, and how are these two angles related? 30 degrees and 60 degrees add up to what? They add up to 90 degrees. So that makes these two angles what? Complementary. Complementary. We are now going to talk about the cofunction identities, which represent the third group of basic trig identities. Remember, we had the reciprocal identities, the quotient identities. Now we have the cofunction identities. Cofunctions are short for complementary trig functions. By the way, I should technically write these out fully, but here I'm using their abbreviations. In case you're wondering how these were related, these are pairs of cofunctions, sine and cosine. They represent a pair of cofunctions. Tangent and cotangent, a pair of cofunctions. Secant and cosecant, a pair of cofunctions. So in case you're wondering, well, how are these related? Sine and cosine, tangent and cotangent, secant and cosecant. Well, I'll give you an example. The secant of 30 degrees will be the cosecant of 60 degrees. And the secant of 60 degrees will be the cosecant of 30 degrees. Again, that's because we're switching the adjacent and opposite sides when we switch angles. Cofunctions of complementary angles are equal. Now you can write out a whole bunch of cofunction identities, but it's easiest to remember this principle. Cofunctions of complementary angles are equal. So for example, the sine of 30 degrees is equal to the cosine of 60 degrees. These were both equal to 1/2. 30 degrees and 60 degrees are complementary angles. Sine and cosine are cofunctions. Cofunctions of complementary angles are equal. The sine of 30 degrees equals the cosine of 60 degrees. Again, that reflects the fact that when we switch from one angle to its complement, we're switching the adjacent and opposite sides. All right. So how can we write out the cofunction identities? And bear in mind that these go beyond acute angles and even right triangles. So this will apply even if theta is 1,000,000 radians or -6 radians. This applies where theta is any real value. You could think any angle in degrees or any angle in radian measure, any real number, really. The cofunction identities, how can we write out some of these? There are a whole bunch of them. If theta is measured in radians, then for all real values of theta, these will be true. These two statements will be true. The sine of theta will equal the cosine of its complement. I claim that pi/2 minus theta is the complement of theta. If we extend the idea of complementary angles to any pair of angles whose measures add up to 90 degrees or pi/2 radians. So theta doesn't have to be acute. Theta could be negative or like 1,000,000 radians. I'm going to extend the definition of complementary angles beyond Math 104. So we can say, for example, -10 degrees and 100 degrees are complementary. Okay, so theta can be any real number, any angle as a real number in radian measure. I claim this is the complement. And why is that? Well, if we add these two together, if we take pi/2 minus theta and add back the theta, what happens? We just get pi/2. Pi/2 minus theta plus theta, that takes us back to pi over 2. So again, I'm claiming that theta and pi over 2 minus theta are complementary in the sense that they add up to pi over 2. Likewise, cosine of theta will always equal the sine of the complement, pi over 2 minus theta. The same is true for secant and cosecant, cosecant and secant, tangent and cotangent, cotangent and tangent. If you have a pair of cofunctions and a pair of complementary angles, cofunctions of complementary angles are equal, or they're both undefined. For example, the tangent of 90 degrees is undefined, so is the cotangent of 0 degrees. Speaking of degrees, if theta is measured in degrees, then basically we replace pi over 2 radians with 90 degrees. The sine of theta in degrees is equal to the cosine of 90 degrees minus theta. Because theta and 90 degrees minus theta are complementary. They add up to 90 degrees. Likewise, the cosine of theta equals the sine of the complement, 90 degrees minus theta. Again, we can say the same for secant and cosecant, cosecant and secant, tangent and cotangent, cotangent and tangent. Cofunctions of complementary angles are equal. Now you can see how it's easier to remember the cofunction identities by remembering this statement. Cofunctions of complementary angles are equal because there are many, many cofunction identities. Many things you could write out. All right, so that's our tour of right triangle trigonometry. In our next part, we're going to analyze the unit circle approach, which will be consistent with the right triangle approach, but it's much nicer for quadrantal angles and maybe for angles in other quadrants besides quadrant 1. And that's next time.
Okay, so since today's a question session, why don't we take a break right now? Okay, so let's take a break right now. All right, and so let's return at 8:18. Okay, so return at 8:18. I'm going to pull up some videos also. I think there's a Simpsons video I want to pull up. Remember to mute, and I got to record. Okay, so at 8:18, I'm going to try to play up some videos here too. Not quite yet. But any questions? Any questions? All right. So actually, here's some video. Oh, well, the Simpsons. Oh, come on. The writers of the Simpsons. You have Harvard PhDs on there, so they totally know what they're doing. The Wizard of Oz, I don't know. Oh yeah, the Wizard of Oz. Yeah, I don't know. Maybe they really didn't know it. They just kind of remembered it vaguely. All right, that was horrible though. All right.
Hi everyone. We're now going to look at the unit circle approach to trig. The unit circle approach is better for angles outside of quadrant 1. It's much better for analyzing quadrantal angles and also angles in other quadrants. Okay, so here's the setup. Consider an angle in standard position, meaning the initial side is on the positive x-axis. Here's our angle, theta. Now, the terminal side intersects the unit circle here at a point. This here is the unit circle centered at the origin. Now, this point of intersection is very convenient. The x-coordinate of this point gives the cosine of the angle, and the y-coordinate gives the sine of the angle. It's very convenient. Oh, and an extra bonus, something that many of you didn't know, the slope of that terminal side is tangent of theta. Tangent is slope. That's a big breakthrough I got from a student one time, and it's still stuck with me. It's a great way of looking at tangent. Tangent is slope. Now, why are these things true? It really comes down to Sokatoa. So over here, we have our angle theta. Sine of theta Sokatoa, sine is opposite over hypotenuse. Now, for this unit circle, the radius is 1, so the hypotenuse is 1, which means that this side here has to be sine of theta, because sine of theta is opposite over hypotenuse. This has to be sine of theta. This is the y-coordinate of that point. Cosine of theta is adjacent over hypotenuse, so this better be cosine of theta. This intersection point has an x-coordinate equal to cosine of theta and a y-coordinate equal to sine of theta. Oh, and by the way, what's rise over run? It's slope. And what's sine of theta over cosine of theta? It's tangent of theta. Tangent of theta gives the slope of this terminal side. I'll type that in. Slope equals the tangent of theta. X-coordinate is cosine of theta. Y-coordinate is sine of theta. And please make sure not to mix these up, because we usually study sine first in trig. So remember, that's not x, it's y. That's a big source of confusion. Tangent is slope. Now, remember, the x and y coordinates on the unit circle are going to fall between -1 and +1 on both the x-axis and the y-axis. And that corresponds to the fact that both sine of theta and cosine of theta can pick up all real values between -1 and 1, and only those values. In particular, the closed interval from -1 to 1, that's going to be the range of both of these functions, sine and cosine. Tangent, however, is slope. Tangent can be any real number, because you can get 0, positive slopes, 1,000, 1,000,000. The slope can be negative as well. The slope is negative over here and over here. We'll talk about that. Tangent can also be undefined, like at pi over 2. The range for tangent is all real numbers. We'll talk more about range later on. All right, now it's time for the table. And you should be able to write this out on a piece of paper in a minute, easily within a minute. There are nice patterns for the special trig values. Let's look first at sine of theta. Here's the pattern for these key special angles between 0 degrees and 90 degrees. The key special angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Remember, we got these from the special triangles. And these are the related quadrantal angles in quadrant 1, the close by ones. In radians, 0, pi over 6, we skip pi over 5, pi over 4, pi over 3, pi over 2. All right, here's the pattern for sine of theta for these angles. It goes root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. And you can simplify these. Root 0 over 2 is 0. Root 1 over 2 is 1/2. Root 2 over 2 and root 3 over 2 are both simplified. Root 4 over 2 is 2 over 2, or 1. So these here are the values of sine of theta for these special angles. So sine of 0 degrees is 0. Sine of 30 degrees is 1/2. And that's a really good thing to remember. So if a physics professor asks you, and I've heard this done before, if a physics professor asks you, what's the sine of 30 degrees? It is 1/2. That's a good thing to remember. Sine of 45 degrees is root 2 over 2. Sine of 60 degrees is root 3 over 2. Sine of 90 degrees is 1. Now remember, sine of theta corresponds to the y-coordinate of this intersection point on the unit circle. As we increase from 0 degrees to 90 degrees, as we increase, I'll write this in orange, as we increase from 0 degrees to 90 degrees, what happens to the sine value or the y-coordinate? It increases. It goes up from 0 to 1. As we go from 0 degrees to 90 degrees, the sine value, the y-coordinate of this intersection point, increases from 0 to 1. So sine of theta increases as the angle changes from 0 degrees to 90 degrees. Now when we graph, remember that we associate real numbers with radian measure, so I'll use radian measure on the graph. Let's look at Desmos. Let's graph y equals sine of x. You could put sine of theta instead. All right, now what's happening between theta equals 0 and theta equals pi over 2? The sine function is increasing. The sine values are increasing as the angle increases from 0 to pi over 2. We'll talk more about the graphs of sine and cosine later on, but if you remember the graph for y equals sine of x or y equals sine of theta, you'll remember that this graph goes up. The function increases in quadrant 1. And that's reflected in this pattern here. Now, what about cosine of theta? Take a look. This column for sine of theta, it almost seems like magic. You reverse this column to get the column for cosine of theta. And the reason is, the cofunction identities. Remember the cofunction identities. The cofunction identities said that cofunctions of complementary angles are equal. Cofunctions of complementary angles are equal. So that explained why, for example, sine of 30 degrees equals cosine of 60 degrees. Cofunctions of complementary angles are equal. They were both equal to 1/2. Well, going back to the table, look at these patterns. 0 degrees and 90 degrees, that's a complementary pair. They add up to 90 degrees. 30 degrees and 60 degrees, again, they add up to 90 degrees, a complementary pair. 45 degrees is its own complement. 45 degrees plus 45 degrees is 90 degrees. Well, so what? Take a look. Sine of 0 degrees equals cosine of 90 degrees. Sine of 30 degrees equals cosine of 60 degrees. Sine of 45 degrees equals cosine of 45 degrees. The sine and the cosine for 45 degrees are equal. Sine of 60 degrees equals cosine of 30 degrees, and sine of 90 degrees is cosine of 0 degrees. We reverse the sine column to get the cosine column, and that's because these pairs are complementary pairs and the cofunction identities. Now observe, the values for cosine of theta decrease. Why is that? Well, remember, cosine of theta corresponds to x-coordinates on the unit circle. And what's happening to the x-coordinate as we increase from 0 degrees to 90 degrees? Well, the x-coordinate, I'll erase these other pieces here. The x-coordinate here, x equals cosine of theta. The x-coordinate, as we go from 0 degrees to 90 degrees, the x-coordinate decreases from 1 down to 0. Cosine of 0 degrees is 1. Cosine decreases. Cosine of 90 degrees is 0. Also, if you remember the graph for y equals cosine of theta, the graph for y equals cosine of theta, if we look at theta equals 0 to theta equals pi over 2, the cosine graph goes down. Cosine decreases in quadrant 1. That helps explain why these values decrease from 1 down to 0. Okay, like I said before, it's very helpful to remember that sine of 30 degrees is 1/2, because then it's easy to remember that cosine of 30 degrees is the higher value, √3/2. For 45 degrees, you may remember that these two values are equal. For the quadrantal angles, it's convenient to recognize the points on the unit circle. Over here, we have 1, 0. Over here, we have 0, 1. Know which is x, which is y. Okay, now what about tangent of theta? Tangent of theta is sine of theta over cosine of theta by the quotient identities. Tangent is also slope. We'll talk about that. Now, numerically, we're going to use this quotient identity. Tangent of theta is sine of theta over cosine of theta. 0 over 1 is 0. This fraction over this fraction, the little 2's knock each other out. They basically cancel out. 1 over √3 rationalizes to √3/3. This number over itself is 1. Tangent of 45 degrees is 1. √3/2, all over 1/2. Again, the little 2's knock each other out. We have √3. 1 over 0, that's undefined. Tangent of 90 degrees is undefined. Now remember, tangent is slope. It's the slope of the terminal side of a standard angle. So if we look up at the unit circle, erasing all of this, what happens as we go from 0 degrees to 90 degrees? What's happening to the slope? The slope, tangent of theta. The slope is 0 for the angle 0 degrees, and as we go through the quadrant up to 90 degrees, the slope is increasing. 0 slope, slightly positive. Tangent of 45 degrees is 1. Very positive. Slope can be 1,000,000, 1,000,000,000. Tangent of 90 degrees, well, what's the slope of a vertical line? The slope of a vertical line is undefined. Tangent of 90 degrees is undefined. Increasing. 0. Remember, √3 is about 1.7, so this is a bit higher than 1/2. 1. √3, again, is about 1.7, going towards infinity in a way. If you remember the graph for y equals tangent of theta, we actually have a VA here and a VA here. But if you look at quadrant 1, as theta goes from 0 degrees towards 90 degrees, or pi/2 radians, you can see that the tangent values increase. In fact, they increase towards infinity. All right. Now, what about the reciprocal values? And what's the deal with these intersection points on the unit circle? We'll talk about those next time.
First of all, any questions about the table? Any questions about the table? Good
Hi,
thing to
everyone.
know.
We're continuing with
Okay, questions. All right, we're good here. All right. All right.
the table of basic trig values from 0 degrees to 90 degrees. We've talked about the critical columns for sine of theta, cosine of theta, and tangent of theta, but now what about the 3 reciprocal functions? Remember, what's the reciprocal of sine of theta? Careful, it's cosecant of theta. The reciprocal of cosine of theta is secant of theta. The reciprocal of tangent of theta is cotangent of theta. How can we get these 3 additional columns and get a very complete grid with 30 values, by the way, if you count undefined as a value? And again, I claim that you can do this within a minute. I think within a minute. All right, so how do we get from sine of theta to cosecant of theta? Sine of theta to cosecant of theta. We can use the reciprocal identities. Remember, cosecant of theta is 1 over sine of theta. Let's work it out. All right. So to get the cosecant of theta column, Well, the reciprocal of 0 is undefined. 1 over 0 is undefined. The reciprocal of 1/2 is 2. The reciprocal of this thing, remember the unrationalized version is 1 over root 2. The reciprocal of 1 over root 2 is root 2. Moving on up. Moving on up. The reciprocal of root 3 over 2 is 2 over root 3. That rationalizes as 2 root 3 over 3. The reciprocal of 1 is 1. So I claim that the cosecant column is basically given by these values over here. Undefined, going down to 1. All right, now let's say that we wanted to get the values for secant of theta. We could go ahead and take the reciprocals of these values, but now wait a minute. Wait a minute. Let's think about this. How do we get from the sine column to the cosine column? We reversed the sine column to get the cosine column. Guess what? To get from cosecant to secant, we can do the same thing. We flip or reverse the cosecant column to get the secant column. And the reason is, cosecant of theta and secant of theta are cofunctions. Cosecant and secant are cofunctions, just as sine and cosine were back here. So one really nice feature of this table is that to get columns for cofunctions, you just flip one column to get the other. You flip the sine column to get the cosine column. You flip the cosecant column to get the secant column. And guess what? You can reverse the tangent column to get the cotangent column. Maybe reverse is a better word than flip because I don't mean flip fractions. I mean reversing the column. Okay, so again, remember that cosine of theta is x, sine of theta is y. So when you consider the corresponding intersection points, by the way, I'll erase these.
By the way, one comment. See, what I did there, I used the annotate function in Zoom, which is cool, but the marks tend to stay on the screen. That's what I noticed. There's my eraser.
When you consider the corresponding intersection points, remember that the x-coordinate corresponds to cosine of theta, the y-coordinate corresponds to sine of theta. So for 0 degrees, the intersection point of the terminal side with the unit circle will not be 0, 1, it'll be 1, 0. X here, y here. Cosine first, and then sine. Cosine first, and then sine. All right. And by the way, when I talk about this unit circle here, this is what I'm talking about. I'm talking about these intersection points. So for example, for the 60-degree angle, right? For the 60-degree angle, we saw that for the 60-degree angle, the corresponding intersection point was 1/2, which is the cosine value, comma, root 3 over 2, which is the sine value, cosine, comma, sine. 1/2, comma, root 3 over 2. Over here, 1/2 is the cosine value, root 3 over 2 is the sine value, x, comma, y. The big picture, if you consider all these special angles from 0 degrees to 90 degrees, looking counterclockwise as usual. All right, at this point, for 0 degrees, the corresponding intersection point is 1, 0. Remember, the cosine of 0 degrees is 1, the sine of 0 degrees is 0. Cosine is x, sine is y. Likewise, hey look, the sine of 30 degrees is 1/2. The cosine is the high number, root 3 over 2. The 30-degree angle gives us a point that's low and to the right, a low sine value and a high cosine value. low y, high x. The 45-degree angle gives us this point here, where x equals y. And the slope, the tangent value, is 1. For 60 degrees, this time the cosine value is low, it's 1/2. I know that 0.5 isn't that low, considering we're talking about numbers between 0 and 1 here, but it's a lot lower than this guy. Remember, root 3 is about 1.7. This thing is pretty close to 1, actually. Again, root 3 is about 1.7. Over at 90 degrees, 0, 1, the cosine is 0, the sine is 1. All right, cosine, sine, x, y. Cosine gives us x, sine gives us y. 30 degrees versus 60 degrees. I like to call this point the talk radio point. I like to call this point the hippie point. The 30-degree point is the talk radio point, low and to the right, like Rush Limbaugh. The 60-degree point is the hippie point, high and to the left. That's my little joke. That's meant to be offensive to both right-wingers and left-wingers alike. Okay, so 30 degrees, low and to the right, 60 degrees, high and to the left. Again, if you remember that sine of 30 degrees is 1/2, the low number, cosine of 30 degrees is that high number, root 3 over 2. For 60 degrees, they're switched. For 45 degrees, these values are equal. And again, for the quadrantal angles, just be really careful what point you're talking about. Remember that this point is 1, 0, and this point is 0, 1. Now, speaking of the 90-degree angle, there's a really great trick that some very clever students came up with. All right, this is a great trick over here. A couple of students came up with this. For the 90-degree angle, pi over 2 radians, sine of 90 degrees is 1, cosine of 90 degrees is 0, tangent of 90 degrees is undefined. Can you see why this, the way I wrote these 3 abbreviations here, really helps us? Sine of 90 degrees is 1. I is the Roman numeral for 1. Cosine of 90 degrees is 0. The O here looks like a 0. Tangent of 90 degrees. Why an A there? Well, if you graph y equals tangent of theta, what happens at theta equals 90 degrees or pi over 2 radians? You get an asymptote. Theta equals pi over 2. Maybe x equals pi over 2 is better. Yeah, x equals pi over 2, vertical asymptote. There's also another vertical asymptote at x or theta equals negative pi over 2 over here. We'll talk more about these later on. All right, so for 90 degrees, because I know that mentally we might be too lazy to move from here to here, right? Let's get straight to the point. Literally straight to the point up here. 90 degrees, sine of 90 degrees is 1, cosine of 90 degrees is 0, tangent of 90 degrees is undefined. That's why we have an asymptote at x equals pi over 2. Again, tangent is slope. A previous hint over here, remember tangent is slope. The tangent values, it's 0 here. It's root 3 over 3 for 30 degrees. Okay, root 3 is about 1.7, so this is about 1/2, a bit higher. Tangent of 45 degrees is 1. Sine over cosine gives us 1. That's the slope of this blue line segment over here. Tangent of 60 degrees, this over this, that's root 3, which is about 1.7. Tangent of 90 degrees is undefined. It's kind of like infinity if you're coming in counterclockwise here. Again, tangent is slope. What's happening to tangent? It's increasing. 0, a bit more than 1/2. 1, about 1.7, going towards infinity, corresponding to the fact that tangent of 90 degrees is undefined. So the table demonstrates all these wonderful patterns that all make sense and they're all consistent. Next time, we're going to brave into the other quadrants, 2, 3, and 4. and talk about the related angles in other quadrants. That's next time.
Okay. Any questions? I know some people like to draw the whole circle. That's fine, but actually you don't have to if you understand the sign patterns, which we'll talk about maybe next week. Questions so far? Questions so far? We have the final video next, and then I'll take questions. All right? Questions. All right. $50-minute video.
Hey everyone. Last time we talked about this tour from 0 degrees to 90 degrees, basically through quadrant 1. Now we're going to extend to other quadrants. All right, so what are the related angles in other quadrants with similar trig values? We're going to talk now about reference angles and what I call brothers. You can call them sisters or siblings, but for convenience, I'll call them brothers. Okay, so the reference angle for a non-quadrantal standard angle, so an angle in standard position, but not a quadrantal angle. So not including 0, pi over 2, pi, 3 pi over 2, and so on. A reference angle for a non-quadrantal standard angle is the acute angle that its terminal side makes with the x-axis. All right, so let's get straight to the point. Over here, we have this 30-degree angle. I like to label the intersection point between the terminal side and the unit circle with the angle measure. Here, this point corresponds to 30 degrees or pi over 6 radians. The reference angle for this 30-degree angle is 30 degrees. The reference angle for any acute angle will be itself. Because, well, by definition, the reference angle is the acute angle that the terminal side makes with the x-axis. For an acute angle, the reference angle is always itself. But 30 degrees is also the reference angle for the 150-degree angle. The terminal side hits the unit circle at this point, and again, the terminal side makes a 30-degree angle with the x-axis. Likewise, for 210 degrees, we have a 30-degree angle between the terminal side and the x-axis. For 330 degrees, we have a 30-degree angle between the terminal side and the x-axis. So all 4 of these angles here, I call brothers because they share the same reference angle, 30 degrees. Some books might call these co-reference angles, which actually does make a lot of sense because we could say that co-reference angles share the same reference angle in the same sense that coterminal angles share the same terminal sides in standard position. So we can think of these brothers as co-reference angles more professionally, although the term co-reference angle is not quite standard. It makes sense, but it's not quite standard. And frankly, I think the term brothers is more evocative. All right. Again, brothers, my term. You can call them sisters or siblings, or if you're a mathematician, co-reference angles. These are angles that have the same reference angle. Now, again, brothers have to be non-quadrantal. Quadrantal angles are different. In fact, I can tell you right now, quadrantal angles will have basic trig values that will either be 0, 1, -1, or undefined. The trig values, the basic trig values for a quadrantal angle will be these guys. All right. Anyway, brothers are really for non-quadrantal angles. So you won't see these values actually. Except, no, actually tangent. You do see that tangent of 45 degrees is 1, for example. So with some exceptions for tangent, for the most part, you don't see these for non-quadrantal angles. You do sometimes see these for tangent and cotangent. Okay. Now, how do we determine these various brothers? By the way, brothers include coterminal twins. For example, you might notice that the point here for 330 degrees is the same point as for -30 degrees. And the reason is that these 2 angles are coterminal, and they share the same intersection point here. So brothers include the coterminal twins. Actually, twins is a misnomer. Every angle has infinitely many coterminal angles. So twins is too restrictive. Every angle has infinitely many coterminal angles. All right. Back to brothers. All these are brothers, coreference angles. Now notice here in radian measure, there's a nice pattern. For example, pi over 6 here, right? That's acute. That's an acute special angle, pi over 6. What's his famous brother in quadrant 2 in radians? And this is one reason why we may prefer radian measure to degree measure. You might think you prefer degrees right now, but actually radians make it easier to hop from quadrant to quadrant. Who's the famous brother for this angle in quadrant 2? 5 pi over 6. 5 is 1 less than 6. How about quadrant 3? The famous brother in quadrant 3. 7 pi over 6. 7 is 1 more than 6. What about the famous brother in quadrant 4? That's positive, because negative pi over 6 is also pretty famous. But the famous positive brother in quadrant 4 is 11 pi over 6. How is 11 related to 6? 11 is 1 less than 12. 11 is 1 less than twice 6. So those are shortcuts to get brother angles. And by the way, why does that make sense in the case of the pi over 6 family? All right, well, I'll bring up this picture again. Actually, what I'll do is I'll take this picture here. I'll shrink him a little bit. Shrink him a little bit. And I'll bring the computations up here. All right, there we go. Pi over 6. So that's our reference angle. It's acute. Reference angles are always acute by definition. 5 pi over 6. Why is this 5 pi over 6? Well, how do we get this angle? We go around half a revolution, that's pi radians, and then we backtrack. We go clockwise by pi over 6 radians. We subtract pi over 6. So to get this angle over here, what do? Pi minus pi over 6. Pi minus pi over 6. We want a common denominator. Pi is 1 pi. 1 pi is 6/6 pi. What is 6/6 pi minus 1/6 pi, which is what this basically says. It's 5/6 pi, or 5 pi over 6. The shortcut? 5 is 1 less than 6, because it follows this algebra. What about the 7 pi over 6? Why is he the famous brother in quadrant 3? Well, here I'm going to erase a bunch of this stuff. So here, for 7 pi over 6, we want the pi, half a revolution, plus pi over 6. We want to revolve counterclockwise a bit more, rotate a bit more. What's pi plus pi over 6? And I know students have trouble with fractions and pi, but think through it carefully. Pi is 1 pi, it's 6/6 pi. What's 6/6 pi plus 1/6 pi? It's 7/6 pi, or 7 pi over 6. Take it calm and steadily, you'll get it. Why the 11 pi over 6 in quadrant 4? If we want the positive angle and not, say, negative pi over 6, which is coterminal. All right, this time we want to consider not 1 pi, we actually want to consider, I'll put this in orange, we want to consider 2 pi. That's a full-blown 2 pi radians, a full counterclockwise revolution. And then we're going to backtrack. We're going to go clockwise by pi over 6, the reference angle. Remember, 30 degrees is pi over 6 radians. The reference angle is pi over 6 radians, or 30 degrees. What is 2 pi minus pi over 6? Let's do the algebra or pre-algebra. 2 pi is 12/6 pi. What is 12/6 pi minus 1/6 pi? It's 11/6 pi, or 11 pi over 6. So, maybe this is the Corleone family from The Godfather. What is the famous family of brothers with reference angle pi over 6 radians? Between 0 and 2 pi radians. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. These might be the Corleones from The Godfather. 4 brothers. These are the famous brothers between 0 and 2 pi radians where the reference angle is pi over 6. Okay, now what about the pi over 4 family? The Simpsons. What are the 4 famous brothers with reference angle pi over 4 between 0 and 2 pi radians? Follow a similar pattern. I'll give you a few moments. If pi over 4 is in the upper right, quadrant 1, who are the famous brothers in quadrants 2, 3, and 4, following this pattern? Go. All right, think you got it? Let's see. Pi over 4 in quadrant 1. 3 is 1 less than 4. 3 pi over 4 in quadrant 2. 5 is 1 more than 4. 5 pi over 4 in quadrant 3. 7 is 1 less than twice 4. 8. So 7 pi over 4 here. What about the pi over 3 family? The famous special angles between 0 and 2 pi radians with a reference angle of pi over 3. There are 4 brothers with that property. Go. Follow this pattern. All right, think you got it? Pi over 3, 2 pi over 3 here because 2 is 1 less than 3. 4 pi over 3 here, 4 is 1 more than 3. 5 pi over 3 here, 5 is 1 less than twice 3, 6. Now, it's really great that this trick works for pi over 6, pi over 4, and pi over 3. Actually, it doesn't work for other angles, like pi over 5. Well, let me think about that for a moment. Pi over 5, pi over 5. Actually, come to think of it, that would work. That would work for pi over 5, pi over 7, pi over 8, pi over 9, pi over 10. Actually, that would work. So for example, if this is pi over 10, 9 pi over 10, 11 pi over 10, 19 pi over 10. However, there is another trick with reference angles where actually it wouldn't work for pi over 5 or pi over 10. That's another trick I'll describe later in the chapter. But actually, this works for pi over 3, pi over 4, pi over 5, pi over 6, pi over 7, and so forth. All right. Coterminal twins, remember, have the same trig values, including the signs. So, for example, 5 pi over 3 is coterminal to negative pi over 3. They're going to have the same sine value, cosine value, tangent value, and so forth. But then, why is it that we care about these brothers or sisters or co-reference angles? Even the ones that aren't necessarily coterminal in the same quadrant. Well, here's the thing. It turns out that all these angles in the same family, all these brothers, they're going to have the same trig values, the same sine value, the same cosine value, the same tangent value, and so on, in absolute value, meaning up to the signs. The trig values could actually differ by signs. Why do we care about brothers? Brothers have the same basic trig values up to, that is, except maybe for, the signs. In other words, the basic trig values between two brothers are the same in magnitude or absolute value. They can only differ at most by signs. All right. So we're going to talk more about this sign issue, SIGN, positive and negative, next time.
And actually, that'll be next week. Okay, so we'll get to the other quadrants, the signs, SIGNS, positive, negative, for trig functions. That'll be next week, right? Because we can spend the rest of the day talking about homework. We'll have our nice homework session on Thursday. The homework for chapters 2 and 3, no trig. The trig is not due this week, but keep up, all right? Chapters 2 and 3 will be due on Friday. On the homework, I think many of you know this basic trig. Just keep on going until you get confused. Then maybe next week will help. All right. Any questions? Any questions? That completes the last new video for today. I think I have my remaining videos for next Tuesday up already. I just have to rename them. But yeah, so I have my trig videos up anyway. All right. Okay, so let me all right, it's 9:03. All right, now, first of all, are there any general questions? Any general questions before we enter our homework session? Any general questions before we enter our homework session? Now, students have told me that they really appreciate it if we keep recording, but if for some reason you want me to pause the recording, let me know, like by private chat, okay? Otherwise, we'll proceed with the recording. Okay, no further questions. Okay, so we'll proceed recording. Okay, we're going to continue recording. All right, so we're now going to enter our homework session. All right. Okay, so I have my answers here. Okay. And let me grab the questions. All right. There we go. Okay, so with the homework 2. All right, there we go. Yeah, go ahead and enter the requests in chat. Well, I'll follow the order. All right, so let's follow. I mean, it depends. If there's some clustering, I might follow the cluster, but I'll basically try to follow the order. All right, so let's start with 276. Oh, I remember that one. That's a snake, isn't it? Yeah, it's a snake. It's cool, but it's a little weird because we have a cubic. All right, it's cool when you see it though. Now, of course, you can use things like the sign chart method or the test window method, but the coolest way to do it is the graphical method. So here's the idea. First of all, we want to know the domain of f. All right, so what's the deal? We want to know when this thing is real. F of x is real if and only if the radicand is, that long word, non-negative. Non-negative. I got to stick this in here. Execute purple. X cubed minus x. Maybe move these guys. Oops. Ugh. All right. X cubed minus x squared is non-negative. So a little awkward, but all right. So f of x is real if and only if the radicand x cubed minus x squared is non-negative. All right. So here's the deal. As I did with these quadratics, see, quadratics graph as parabolas. Cubics graph as snakes, right? So let's consider the graph of y equals x cubed minus x squared. Oh, yes, by the way, I did some problems maybe last time. I might refer students to videos and then do them at the end today, perhaps. All right. Remember, I normally answer questions after class, so you might be able to get the answer to your favorite or least favorite question after class in my previous videos. All right. Okay, y equals x cubed minus x squared. Now, it helps to factor, right? Helps to factor. Y equals GCF is x squared. Okay, and then we have x minus 1. All right. And of course, 0 is the 0 here. 1 is the 0 from here. Okay, so let's consider the corresponding graph. All right. We're graphing that polynomial cubic radicand. All right. Leading term is x cubed. It's a rising snake in the long run. It's just a basic sketch. All right. The first x-intercept we encounter is at the origin. The multiplicity is 2, even. We bounce. We bounce off the origin. We have some sort of min point over here. We go up at x equals 1. Because the multiplicity is 1, we cut, and the snake looks like that. All right. We can do this on Desmos. Y equals x cubed minus x squared. All right. Let's zoom in a bit. Yeah. So it's a snake, goes up to the origin, goes down, dips, min point there, and it cuts through 1, 0. Okay, so that's a very nice graph. Okay, but my picture not as nice, but gets the key issues. Now I want to where are the y coordinates non-negative, right? So these are the y coordinates here. These are the y coordinates. Where are the y coordinates non-negative? I'm going to do this in green. Make it hairy. I want these y coordinates over here. Non-negative includes 0. I do want the intercepts. I don't want these guys here, but look at this, folks. I do want to pick up this guy. The origin, that island. So it's kind of weird, all right? So what are the corresponding x values we pick up? We pick up 0 and everything from 1 on. Everything from 1 on. So in my answer sheet, right? Now, I actually use set builder form because it might be more familiar. The set of all x in the reals such that x equals 0 or x is greater than or equal to 1. If you want to use interval form, then that island at 0, that'll be a singleton set, right? Where the zeros and braces union, bracket 1, comma, infinity, parenthesis. Okay, that's a union of a singleton set and an interval form. We've never seen that before. All right. All right, that's 2-7, number 6. Okay, any questions? Any questions? 2-7-6. I'm sure many students have questions about that. All right, if you got to that, right? All right, so, okay, so going to the 3-4 section, number 6. All right. Oh, and please, I want to remind people, and I'll remind you of this next time as well, okay? Now, when I say additional problem, the additional problem is this piece here. These are required, okay? Now, I mean, maybe, you know what? I better warn people of that next time. I mean, and we work it in class next time if necessary. So sorry, folks, if you didn't realize that, but these are required. Normally, the additional problems are optional, but my additional problem here is only that blurb. This whole thing is required. Okay, I want you to do this. Sorry, that's gonna be some work, huh? If you didn't know that. Okay, okay, 3-4. Oh, okay. Well, I'll make a deal with you. Could you give me one of these? Okay, and then maybe we'll do one of these if someone wants a second one, perhaps. Okay. Well, I see a request for A. Why don't we say, okay, A and C, okay? Let's do A and C for now, and then perhaps save the others for later or on Thursday. Okay, so let's try A and C. All right. Wait, what? No. No, because what I'm doing is I'm asking the student over here. We're okay. Okay, so lots of questions. All right, so A. All right. Okay. And you know what? This is an example where parentheses might be helpful. You know, I'm thinking that maybe I should retype this where the parentheses are on the X, because a lot of students get confused. But when books have that, the assumption is that you're only taking log base 5 of X, not all of that. That's a very common mistake. But you know, this is an example of why it can be very helpful to clearly indicate what the argument is, okay? The log does not apply to the -5 here, all right? I'll work this problem. Start by isolating the log. We add 5 to both sides. I'll do it directly. Okay, we want to isolate the logs. We have log. I like to curl my L so they don't look like ones. Log base 5 of X. Okay, it's not of X minus 5. A lot of students get confused by that. Okay, equals -2 plus 5 is 3. Okay, and then let's do the zigzag. Let's put this in exponential form. Now you could do base 5 on both sides, but I don't think that's quite as familiar to students. All right, you could do that. Let's do the zigzag. Zigzag says 5 to the third equals X. 5 to the third equals X. 5 times 5 is 25. 25 times 5 is 125. I don't blame you if you need your calculators for that, but with time you'll get used to this. 5 cubed is 125. Okay, I can turn it around, but your final, well, bear in mind, we should check, right? If you plug in 125 here, all right, 5 to the what is 125? That's 3. So 3 minus 5 is -2. It checks out. It checks out. The fact that X is positive, the argument is positive here, that's a big help. Okay, it's likely that this works out. It does work out. So the solution set is this. It simply consists of the 125. Although remember, sometimes you can get 2 or 3 solutions or whatever. You would just have one solution. Any questions? Any questions? Again, in future semesters, I might want to put parentheses there because that has befuddled students before, and I don't blame them. But I should tell you that when books have something like that without the parens, it's assumed that it's read like that. Yeah. So maybe there are good reasons why I didn't put them in. C. Okay. I'm sure B also befuddled some people, but let's do C. That was requested. All right. So log base 3 of this 4th power equals 12. And this saves you, assuming X is greater than a quarter. Okay, now I'm going to go ahead and erase this. Okay, so right off the bat, this is going to help out a lot. What can we do with the 4? Because those of you who are freaking out, oh my gosh, do I have to work out the 4th power? No, you don't. What can we do with the 4th power? The 4 up there. What did the Rock, Dwayne Johnson, what did the Rock used to do? The Rock smack down by the power rule, okay? Use the power rule. I'm sure you don't want to take the 4th power. So we have 4. 4 log base 3 of 4x minus 1. Equals 12. All right, any questions about that? The power rule, smackdown rule. Now you might be wondering, why am I bothering you with, I'll put this in brown, okay? Why did I put this assumption here? Actually, I was being your friend. I was being nice to you. Because as a result of this assumption, what that ends up meaning is that this thing here is positive. It's positive value. If X is greater than a quarter, this thing is positive, which means that you don't need absolute value. Okay. See, if you didn't have this assumption, right? If you couldn't assume this or conclude this, then you would need absolute value. So if I had not put this note here, you would have needed absolute value, and it would have made it a somewhat trickier problem. That absolute value issue does catch you once a couple years or so. All right. Anyway, we have this. We don't need absolute value. All right. Well, we want to isolate the log, divide both sides by 4. Oh, I understand. Okay. And proceed from there. Okay. So I'm being told that this is a good hint. If you wish to come back to this, we can. But I think that's the key thing, right? Again, we can come back to this if desired. And remember, we have all of Thursday. All right, folks. Let's have a vote. Because my stats people said the same thing, and I'm starting to think the same thing too. You're learning more from having homework sessions instead of tests, aren't you? I'm wondering if I want tests when I go back on campus. We're learning more from the homework. Yeah. That's mind-blowing. When I go back on campus, I might not want tests. I think you learn a lot more from these homework sessions. Yeah. Wow. Okay. Anyway, let's go and proceed here. Yeah, no one's going, we want tests, because then they'd be probably stoned or something. Stoned by other people, I mean. All right. Okay. All right. 2, 4. All right. Well, you're right in the sense that, I'm braver on the homework. So I'm willing to push people more on the homework. On exams, I mean, I'm willing to put a slightly harder problem, but I don't really push people on exams. But you're right that on the homework, I don't mind throwing you a curve, and we can talk about it. Yeah. All right. Let's. Oh yeah, I remember it was over here, right? So, borrowing questions here. We can come back. 2, 4, 10, and 2, 5, 8. But I think someone mentioned 2, 5, 8. Yeah, someone 2, 5, 8. I guess may have been done last Thursday. So let's do 2, 4, 10. Okay, I can do at least one of these. Okay, and students, thank you for making those notes. Sometimes I forget. Okay, so 2.4, number 10 here. Find the complex zeros of G, where G of T equals 3C squared minus 4T plus 5. Oh, I see. Okay, so you're pretty much going to need the yes, I can take some trig questions, maybe at the end, because I think people appreciate the chapter 2, 3 questions first, but then we can do chapter 4 questions at the very end. All right, because remember, no trig is due this week. Now, of course, you should keep up, but no trig is due this week, so I think students would rather see the 2, 3. That's due this week. All right, so this is the quadratic formula. All right. Because remember, I'm assuming the zeros are imaginary. Generally speaking, if you think the zeros are going to be imaginary, then old school factoring probably isn't going to help you. Okay, so I'm going to go straight to the quadratic formula. T, technically, equals, all right, remember it's the opposite of B, plus or minus the square root of the discriminant, which tells you a lot of the story, right? It discriminates between different cases and scenarios. B squared minus 4AC all over 2A. Okay. Of course, I don't sing as well as that teacher. I hope that teacher's song is going through that head, the kid on the beach, right? All right, so I'll go ahead and plug in directly. You know this, right? So opposite of B, now careful, B is the opposite of 4. So we're taking the opposite of 4. That's going to be positive 4, all right? Plus or minus the square root of the discriminant. Well, I don't want to bore you. Let me quickly figure it out. So the discriminant, I'll write it here. The discriminant, delta, the discriminant is going to be, okay, B squared minus 4AC. That's the square of negative 4, right, which is positive 16, remember, minus 4AC. Okay. Remember, the result here has to be non-negative. You're squaring, all right? So that's going to be positive 16 minus 60, right? So that's, oh, yeah, this is going to be tricky because you have to simplify that radical. Equals negative, is it 44? Really? Well, it's been so long. It's been so long since I've done these that. All right, negative 44. Oh, okay, right. So it's going to be 2I root 11. All right, okay. All right. So anyway, so we have that. Okay, so equals, I know it sounds so silly. It's like, these are my homework problems, but I forget my own answers. Okay, equals, okay, 4 plus or minus the square root of negative 44. See, folks, some of you may have gone, hey, I wanna work out the discriminant. I want to see what's going on. And you would have found that the discriminant is negative 44, and then you go, wait, the discriminant's negative. I cannot do old school factoring. That means I'm going to use the quadratic formula, and you know that the negative 44 goes in here. Okay, now that's all over. It's all over. Don't make it too short. A lot of students do this. Don't make it too short. All right, all over 2 times what? 3. Okay. As I said before, a lot of you might actually want to write A, B, and C separately, right? Before you do that, right? So we had A equals 3. B equals negative 4. Negative 4. Negative 4, right? C equals 5. Okay. So a big reason why you might have wanted to write the parameters out separately is that a lot of students would forget that B is negative 4. Here, it doesn't matter so much, but here it does. Yeah. Okay. So anyway, how do you simplify this thing? This is where you might have gotten tripped up. Equals, all right, now on the bottom you have 6. That's okay. 4 plus or minus. Okay, now first of all, let's deal with the fact that we have a negative radicand in here. I'm going to write this as I root 44. The principal square root of negative 44 is I root 44. Okay. Now you could put the I here, but if you do that, make sure not to extend that radical. Okay. If I see that radical over that I, don't make me get my ruler, right? Okay. Now, however, root 44 itself needs to be simplified. And some of you may have forgotten how to do this. Okay. A lot of you may have gotten tripped up here. So how do you simplify in blue? How do you simplify root 44? Let's review our algebra 2. What's the largest perfect square that divides 44 nicely? That's a factor. Well, 4. 44 is 4 times 11. Which breaks up. It's root 4 times root 11. Root 4 is 2. So we get 2 root 11. The way I often think of it, 4 is the largest perfect square that divides 44. Okay, it pops out as a 2. And this simplifies as 2 root 11. Okay, so equals 4 plus or minus. Now we have the I there, all right? Root 44 is 2 root 11. Again, I'm very paranoid about putting the I at the end because so many students extend that radical and I'd have to mark off for that, right? Okay, because root 11I, that's no good. That's no good if you put the I inside there. All over 6. All right. But we're not quite done yet. We're not quite done yet because we can factor a 2 out of the top. And we're going to get a simplification. 2 times the quantity, 2 plus or minus I root 11. All over 6. All right. And then old school cancellation, division, right? I'll use red here. Oops. It's our cancel color, red. Okay, now here, remember, 2 is now a factor of the entire numerator. 2 goes into 2 once, 2 goes into 6 3 times. Now, folks, a lot of students like to pull a stunt like that. Don't do it. If you have 2 terms on top or on bottom, don't pull a stunt like that unless you also affect this guy. Actually, it would work if you divide all 3 by 2. That works, but not this and that. All right. And then we're close to done. Wait. Do you have to do it in simplified form? No, I don't specify simplified form. So we don't have to do simplified form. Meaning you don't have to write it standard form. You don't have to write standard form. I want you to simplify this, but you don't have to write standard form. All right. So you get 2 plus or minus, I root 11 all over 3. And I don't think I put that in standard form, or did I? Maybe I did, but no, I didn't bother, right? And in fact, you can use the plus or minus here. That's fine. technically, this is better to write because it's clear that there are two solutions. One problem with the plus minus is that it may not be clear to people that there are two solutions. They might think that you're just unsure. But yeah, 2 plus or minus I root 11 all over 3. Of course, you can rewrite this in standard form. Oh, you're very welcome. Yes, yes. Now, the students are telling me that 258 was in the video. I'm sure you remember. Oh, any questions here, by the way? Any questions here? Okay. 258. Yes, I remember this one. Okay. But, I can do this quickly. I can describe the setup quickly. Hey, folks, you have this kind of nice polynomial. If 4 minus 5i is a complex 0, what else must be a complex 0? The complex conjugate, 4 plus 5i. Now, I may not have stressed this in class, but the factor theorem does work with imaginary zeros. So basically, when you get this factor over the reals, you want to deal with x minus the number 4 minus 5i. I'm basically repeating the video, but I may as well do it here, so you don't have to search it. So x minus the quantity 4 minus 5i, and x is still minus the quantity 4 plus 5i. And you distribute like crazy. All right. So it's a bit tedious after that. Once you get this, you have the concept of it. After that, you're distributing like crazy. All right. All right. First of all, questions. All right. Next up is 262b. All right. Right. 262b. All right. So it's rational functions, by the way. 262b. Ah, yes, holes. Right. I know holes. I didn't flesh out too much in the written notes, especially. I hope the lectures I describe them in more detail. All right. So find the holes. Oh, yeah, and the y coordinates is really a calculus issue, really. So first of all, for this, you need to factor both the top and the bottom. All right. Well, part A kind of forces you to do that. So let's do that. First, you factor out the GCF. Okay. The GCF on the top is what, 6x squared. You can do it piece by piece, but the GCF on the top is 6x squared. When you divide to get the other factor, you get a cutie, right? When you factor, you divide. We have x squared minus 4x plus 4. All right. I'm not sure if this was in the previous video, but let's go ahead and do this. Part B, it's not too bad. All over, and then the GCF down there is 3x squared, right? Yeah, 3x squared. All right. Times, what is that? Divide x squared plus x minus 6. I'm recording, right? Yes, I'm recording. I'd be so mad if I weren't recording. If I were recording, I think I'd have to mute. All right. Anyway, I'll shorten this. Now we still have these cuties to factor. Now the guy on top is actually a PST. Okay. So on the top we have 6. So I'm not going to simplify yet because I want to discuss the cancellations in a moment. All right, 6x squared. All right, this is a PST. If you work out the discriminant, it's 0. We have the square of what? We have the square of x minus 2. Basically, it's half the coefficient on x. All right, all over. Okay, 3x squared times, okay, so that's going to be, it's x plus 3, right? And x minus 2. Actually, for visual clarity, I'll put the x minus 2 first for visual clarity, and then the x plus 3 last. Of course, the order doesn't matter, but this may be clearer. All right, so any questions about that factorization, which was not trivial, right? A lot of students would take several minutes for that. Okay, now let's discuss the cancellations. All right, let's discuss the cancellations. All right, when do we get holes? If we get factors here that get completely canceled out, right? So x squared over x squared, we're going to get a hidden restriction. X is not 0. Okay, when you cancel here, notice we have two guys here, just one guy here. We do get a complete cancellation in the bottom. And by the way, there is one copy of x minus 2 who survives on top. But the bottom line is that as far as holes go, this x minus 2 factor gets completely canceled out in the bottom. Okay, so we have another hidden restriction. Holes normally correspond to the hidden restrictions. All right, so find the holes on the graph. All right, we're going to have a hole with an x coordinate of 0 and another hole with an x coordinate of 2. Okay. So actually, if I want to ask, give me the x coordinates of the holes, which I sometimes did on exams, because the y coordinates are technically limit problems, actually. So as has been mentioned earlier, see, on the homework, I push you more. Now on a test, I might ask for the x coordinates of the holes. They'd be at x equals 0 and x equals 2. And on an exam, that'd be good for that, okay? Now for the y coordinates, that's actually a calculus problem. You basically plug in the 0 and the 2 into the surviving pieces, and then that's how you get the y coordinate. So for example, I'll go ahead and simplify this. Oh yes, I don't blame you. I mean, the y coordinates, that's a calculus problem, right? I'm kind of okay, so I'll do it here. All right. So it's 6 times there's one copy of x minus 2 all over the x plus 3. Hey folks, by the way, we still have surviving x plus 3 factors down there. One comment. What happens at x equals -3? So that's a plus sign. It's a horrible plus sign. Tell me, what happens at x equals -3? We get a what? Not a hole, but a VA. Oh, thank you. Yes, I forgot. 6 and 3. Thank you. Yes. Now that won't affect the some of the features, but it will affect some of the numbers here. So yeah. Thank you. 6 divided by 3 is 2. Thank you. All right. All right. So 2, because you can also cancel with these guys. How ironic that I messed up with the constants. Okay. So 6 divided by 3 is 2. Thank you. Or for the purposes of our analysis, you could have left the 6 and the 3, but why do that? Okay, thank you very much. All right, so with these hidden restrictions, by the way, and again, so remember these hidden restrictions also apply up here, all right? One benefit to writing these hidden restrictions is that they tend to lead to holes, right? And here, they do lead to holes with the equal signs, all right? So basically, you can now plug in the x coordinates into this expression here. Technically, you're taking a limit. You're taking a limit as x approaches 0. Plug in 0, you get what? -4/3. That sounds familiar. -4/3. That's the y coordinate of the hole. You're doing calculus. Plug in 2, see here, you get 0. Okay. But folks, that's not an x-intercept. It's a hole, all right? In fact, I'm going to graph this thing on Desmos. And I know that people, this is also problem number 8 in the homework, but let me bring this over. And I think other people might have questions about other parts of 2 also. So while we're at it, 6 to the 4th minus 24x cubed plus 24x squared. Whoops. Watch those parens. All over 3x to the 4th plus 3x cubed minus 18x. Whoops. 18x squared. All right. All right, folks. Oh, you think, oh, this looks pretty easy. You're too zoomed in. Haha. Gets more interesting, doesn't it? Is that right? 6 to the 4th minus 1 minus. Yeah. And the thing is, oh, you know what? I am going to use zoom annotate. I'm going to use zoom annotate. Yeah, because here's the thing. You might think that's a y-intercept and that's an x-intercept. No. Why don't you have intercepts here? Because what do you have there? You have holes. You have holes. Okay. So I'm going to get the annotate feature. It's been a long time since I've used annotate. Draw. All right. Folks. What? Oh. I got him in the chat box. All right. The annotate function. Do I remember how to use the annotate? Okay, there we go. Okay, so you have a hole. You have a hole over here and over here. These are not intercepts. These are not intercepts. If you have holes at those points, they're not intercepts. All right. You're right. You're right. So you're correct that if you click on the graph, Desmos will recognize that's undefined. Yeah, see that? But you have to click on it. That's right. Otherwise, see if you're a naive student, likewise over here, right? If you click on it, hey, wait a minute, naughty Desmos. Desmos is wrong. Naughty Desmos. See, you're smarter than Desmos. Look, folks, 2 is not in the domain. That's something. Domain. See, Desmos doesn't know that. You are smarter than Desmos. Yeah, but that's interesting though. See, folks, technology can help, but you can be smarter. You are often smarter than the technology, and you cannot rely on the technology. It can be very arbitrary. But I'm so glad that you brought up that point. Desmos knew about this hole, but not this one. Wow, I didn't know that it did split decisions like that. It depends on. Wow. See, technology can mislead you. There's a hole there. Wow. I didn't know that. I didn't know that Desmos messed up like that. All right. Oh, wait. I don't want these. Thank you. All right. All right. So again, x equals 0, x equals 2. That would have been totally fair for a pre-calc class. The y coordinate's a limit problem. But why? Why do we have holes? So students, tell me, why did we have holes at x equals 0 and x equals 2? There are several right answers to this. Give me some reasons why we're undefined there, or why we have holes there. Why do we have holes at x equals 0 and x equals 2? Well, I'll give you some hints. They're not in the domain, right? They make the denominator 0, so we got a problem. We're not going to get a regular point, all right? And the corresponding factors here get completely annihilated in the bottom, all right? They get completely annihilated. You have no survivors. X factors no longer survive in the bottom. X minus 2 factors no longer survive in the bottom. So these explosions are controlled. The guy at -3, you have an explosion. See here? You have a VA at x equals -3. But that's the only VA, the green guy. That's the only VA. And should be dashed. All right. So folks, I've done so much work on number 2. Are there any further questions about number 2? I'll keep this. Let me look down here. Again, so I'll give you about 30 seconds. Look, because number 2 is really key. All right, and number 8 is the graph. Any further questions about 2? All right, and then 8, I want you to graph it. Right. Well, it's gonna be this. It's gonna be this guy, right? Hole here, but see if you see why. Hint: this green line, that's an odd VA. Okay, that corresponds to the fact that we have an exponent of 1 down here. It's an odd VA, meaning the branches go in different directions. Right? Any questions? All right. After that, okay, so 258 we did. 252H. You know, it's really dawning on me in so many ways. My Zoom class is better than my on-campus class. It's been a great class, I feel, but yeah, my Zoom classes are better than my on-campus classes. All right, H. I just want to see where the t minus 3 part in the answer comes from when factoring. Oh, I think I'm multiplying in or something like that. Let me go I'm gonna cheat and go to the answer. Bear in mind, you know, don't be afraid to refer to the answers if you think it'll be illuminating. Look, the homework's for your benefit, right? I want you to learn, right? If the answer sheet helps, whatever it takes to learn, okay? What it was 252H. I might be able to do it just here. Oh, no, it's a short answer. Way back here, it comes from C. Remember C? Is 3 is 0? Well, you put 3 in the dunk tank, you put the coefficients, you should have gotten a 0. Hey, 3 is a 0. Guess what? T minus 3 is a factor. Maybe we just forgot about him. It was from way back in C. Right? So because 3 was a 0, T minus 3 is a factor. That was from part C. Okay. Okay. Oh, yes. So apparently you knew the math. It's just that my homework problem was too long. It was my fault. My homework problem was too long. Who does A through H? Only a sadist, huh? All right. No, it might have been my fault, actually. All right. What's going on? Okay, so 3-1. Okay, and now if anyone interjects, unless someone interjects, I'll go ahead and proceed through these. All right. And by the way, I'll stop at 10:30. All right. So I'm willing to go to 10:30. Of course, you can leave, right? But I'm willing to go to 10:30. All right. 3-1. Oh, okay. Okay. So 3-1, 4, and 5. So here's what I might do. So I might set these up, and then maybe you can, use your calculator and calculate. So let's set these up. 3-1, 4, and 3-1, 5. Let's set these up. All right. So on the day of a child's birth, that sounds like The Godfather or The Simpsons. It's the day of my daughter's wedding, or is it Family? It was Family Guy. On the day of my daughter's wedding, on the day of a child's birth. Oh, I believe 258 wasn't that at the end of last time's? I think it was the end of Thursdays. Yeah. So that'll be Thursday. Yeah, that makes sense, right? I don't think I answered that many questions last week. All right. Anyway, so 3-1 number 4. So this is the hard problem. And by the way, on exams, I would give this to people. I would not have people memorize the regular compound interest formula, but it would be A or F of t equals, and this is from the notes, the principal P times the quantity, so this is number 4, times the quantity 1 plus R over N all to the NT. I'm actually shocked I remember that. Again, I gave this on exams if necessary. All right, let's plug in. So F of, after 8 years, right? So F of 8 years, all right, equals, the principal is $1,700. I'll put the unit, put the unit at the end, okay? 1,700, that's in dollars, times the quantity 1 plus, but here's the thing. If you have annual compounding, that means that N is 1. It's just 1 compounding per year. So you just have to worry about R here. And R is what? What's 4.2% as a decimal? What's 4.2% as a decimal? Good, because 4% is 0.04. So 4.2% is 0.042. I'll type that out, okay? 4% is 0.04, right? So that's the way I think of it. 4.2% is 0.042. So R is, you can put the 0 in front if you wish, 0, 4, 2. Again, n is 1 and t is 8. So I believe that's a setup. I believe that's a setup. Do I have the setup here? 3, oh, it's 3, 1. It's 3, 1. Number 4. Okay, well, I don't have the set. Absolutely show work. See, okay, absolutely show work like that. Of course, the answers are here. There's no way I would accept answer only. Come on, I'm giving you the answer. So absolutely show work. You could show this, for example. Okay, and I hope you get the right answer. I hope that's right. All right. 5. Let's set that up. Yeah, okay, let's set this up. Okay, so on 4, okay, so on 5a, here's the difference. So it's going to be f of 8. Oh, let me use a different color. I'll use purple. F or g of 8. If I want to be a stickler, I should really use a different letter. G of 8 equals, it's the same principle. Quantity 1 plus r is still 0.042. You could put a 0 in front. But this time it's monthly compounding. Monthly over, monthly is 12. N equals 12. That's the difference. And all to the nt, so all to the 12 times 8, which is 96. In fact, I recommend you do that first. 12 times 8 is 96. Because remember, when students do this in their calculators, they forget to group the exponents. So I recommend you replace that with 96. Okay, so it's a bit different. There are 96 compounding periods in 8 years. And that's the setup for that. Continuous compounding, that's PERT. You use the PERT formula. E is a number. Okay. So unless you really would like it, I'll leave that hint with you, okay, PERT. That's continuous compounding, all right? Same principle, same R. T is 8, E is a number. Okay, so, and so on. All right. Okay. Okay, so let me go back and forth. So remind me that I still have a few more of these to do, but I want to go on to 264. Okay, but remind me. Oh, sorry. Okay, sometimes I private chat. Okay, let's see. What's next? 264. Yeah, it's this one, right? Oh, yes. So it's okay. On the one hand, it's a concept problem that forces you to think carefully about what's going on, but it's very little work. Here's the bottom line. All right. In fact, here's a hint to you. What is x to the 8th divided by x to the 2nd? What is x to the 8th divided by x to the 2nd? It is x to the 6th. What did you do to the exponents? When you divide powers of x, you subtract the exponents. And in general, it's true that an 8th degree polynomial divided by a 2nd degree polynomial gives you a 6th degree polynomial. All right. So the graph resembles the graph of a polynomial of what degree? 6. All right. So what does this look like in the long run? Let's graph this thing. Y equals x to the 8th. Oops. minus 7x to the fifth all over x squared plus 1. Ah, see. Now, I know he's kind of excited in here, but if you zoom out, you see overall it's a bowl. It's a bowl in the long run, okay? It's at 6 degrees. All right. So if you do the long division, you're going to get a 6-degree quotient, okay? But it was really a concept problem. That's all I needed from you. So yes, on this, I'll accept answer only, but I'm sure you were curious why the answer was the way it was. Yeah. Yes. All right. Now, before I go back to the other chapter 3 problems, you're welcome. Yes. Before I go back to the other chapter 3 problems in chat, anything else? Anything else? I will go to 334. All right, I'll go to 334. And I'm going to save this. Yeah, I'm glad I'm saving my notes here. Okay. By the way, those of you who use a Mac like me, remember that if you want to save these things and use markup toolbar, remember you need PDF, not PNG, PDF. All right, without using a calculator. Okay, all right. So log base 3 of 3. What's log base 3 of 3? 3 to the what is 3? 3 to the what is 3? 1. Okay. What's log base 3 of 9? 3 to the what is 9? It's 2. I think you know the answer to my next one, but let's see this. What is log? What is log base 3 of 27? That's 3. Okay, so just a couple more of these. In blue, log base 3 of 81. Well, you may remember 81 is 9 squared. So it works out to be 3 to the 4th. It's 3 squared squared, right? All right. Oh, by the way, not good to have too much copyrighted stuff on there. Okay, all right, 3 to the 4th. All right. So log base 3 of 81 is 4. Because 3 to the 4th is 81. Okay, now one more, and then some of you are getting bored, going, "What are you getting at?" Okay, it's just coming. Okay, some of you know what I'm getting at, right? Log base 3. If you multiply by that by 3, it's 243, which is 3 to the 5th is 343. Therefore, if you want to approximate log base 3 of 200, it's somewhere between, okay, well, 3 to the what will be 200. Tell me about this number. Tell me about this number. The number that fills in the box, it's a number between 4 and 5. And that's the answer that you can give. Wait. Yes, it must lie between 4 and 5. So even if you had just a very basic calculator, you should be able to do that. You know what? A graph might be helpful. Okay. Remember, by the change of base property, log base 3 of x. Okay, so what is log base 3 of x? Y equals, it's ln of x over ln of 3. That's just by the change of base property. It's this guy. Here's the point, 3 comma 81, 4 comma 243. Oh, I really have to change the axes though. Yeah, I got to change the axes. 300. Wrong axis. Wrong axis. All right. Oh, no, well. It might be just, nah, it's just hard to graph. It's just hard to graph. Okay. Oh, by the way, what is the value? Log base 3 of 200, that's ln of 200 over ln of 3. So it's about 4.8. Yeah. All right, anyway, all right. That's 334 is a concept problem, right? Okay. Although it'd be nice if you showed some work. Explain to me why that is. Right? Okay, so I'll go to this last one, 3.5 1D. Yeah. Oh yeah. This always gets people. All right. So here's the trick here. Substitution. I think substitution will help here. U equals e to the x. We're hoping that's a square, is it? If u is e to the x, what's the deal with e to the x all squared? How can you simplify e to the x all squared? Okay. I know you're not used to this with variable exponents. When you raise a power to a power or exponent, you do what with the exponents? You multiply them. The square of e to the x is e to the 2x. This is that. It works out. Okay. But this isn't even a cutie. It's just it's a quadratic form, but it's not even a cutie. Yeah. Okay. He's nicer, right? Because when you do the substitution, you get u squared minus 4u. Whoops. Equals 0. You can factor. All right. U equals 0. Or u equals 4. Oh, am I done? Am I done? Oh, these look so nice. These look so nice. Am I done? No. Sub back. E to the x equals 0 or e to the x equals 4. But wait a minute. Wait a minute. Can e to the x ever be 0? Can e to the x ever be 0? Look at this. Y equals e to the x. Y equals e to the x. Oh. I'm just kidding. Y equals e to the x. All right. Now, in spite of what you see here, is e to the x ever 0? Is e to the x ever 0? No. No. Right. Yeah, because this graph does not touch its HA. And this is a graph that does not touch its HA, right? Some graphs do. This graph does not. Which means, e to the x equals 0, dead end. you will not get any solutions from that equation. You may as well have 1 equals 2, right? Dead end. However, e to the x equals 4, proceed from there, right? You take natural log of both sides, okay? And I think, yeah. So you get x equals ln of 4. We take natural log of both sides. Okay. And you put that in the solution set. Yeah, over here. ln of 4, which is approximately that.
So you don't have to square it because of the u squared.
Well, bear in mind, you're doing the factoring here, right? So e to the 2x is u squared, and you're factoring. So after this point, there are no more squares.
Okay. See, when I originally saw the factor hit, I did e to the x and then open parentheses e to the x minus 4, and I just stopped there.
Oh, that works also. Yeah, this works. Oh, that was very clever, because a lot of students don't see that. But no, this leads to the same thing, right? Even more directly. Equals 0. And by the zero factor property, we have e to the x equals 0, or this equals 0, which is equivalent to this. E to the x equals 4.
Gotcha.
Yeah.
Thank you.
Very good. No, I'm very impressed you factor that directly like that. A lot of students mess this up. You know what? A lot of students put a 2 here. That's bad. That's the wrong thing. Yeah, but no, excellent factoring. And you know what? I would often put a question like that on an exam, and that's a good separator. That really gives me the A students, the people who really get A's on the exam. Yeah, good problem. And then it's a routine skill in calculus. Let me check the chat here. We're at 10:04. We have a good time. Okay, going to 355. Oh, any questions, by the way? Any questions? All right, 355B. All right. What time does that correspond to the nearest minute? Oh, yeah. That's a tricky problem, isn't it? Okay, you know what? I'm gonna cheat and use 5A, unless you need me to show 5A. Did you? Oh, okay. So you got A, right? You got A. All right. Yeah. Okay. So in a way, this is kind of similar to the degree, minutes, seconds stuff, right? Okay. So how do you go from here to here? This is a good exercise, right? I mean, yeah. How do you go from like a decimal number of hours, afternoon, to an actual time, right? Like this. Okay. So here's the deal. T equals 0 corresponds to noon, right? Yeah. Petri dish T hours afternoon. T equals 0 corresponds to noon. Okay. So if it's 7 hours after noon, we're at 7 something p.m., right? All right. So here's the deal. How do you convert 0.343 hours? Maybe I'll type this. 0.343 hours. Okay. You convert it by multiplying by. Okay, now remember the goal is to multiply by 1, right? We have hours here. You want to put the unit you want to kill off down here. So we want hours down here as well, right? So we can cancel these out. How many minutes are in an hour? How many minutes are in an hour? Answer is 60. So then you can convert hours to minutes. All right, so 0.343 times 60 equals, and that rounds off to 21. It rounds off to 21. So lo and behold, 0.343 hours is about 21 minutes, but it's 21 minutes after 7 p.m., right? Because 7 hours after noon is 7 p.m. We're getting at the 21 there, right? So it's 7 p.m. and then 21 minutes after that. It's 21 minutes after 7 p.m., right? That's how you get that. Conversion. Any questions? All right. Otherwise, there were the other ones that you had. Oh, was that it? Oh, I guess that's it. Come on, the night's young, 10:07. No, you've worked very hard. You've shown real commitment. You've worked very hard. It's 10:07. I'm still up. So at 10:08, I'll call a 3-minute break and see if anyone has anything, okay? Oh, okay, so I see a 356G. Yeah, I got to email people that these are required because students got confused or wishful thinking. All right, G.
I got confused too.
Yeah, I got to send that email out. But then people are going to get mad. Oh, man, but we thought, because these are good problems. You need to know this. Yeah, you see, I had a note, but I forgot that note. Yeah, because, yeah. All right. Okay, so I'm going to do this in green. Green's good now. All right, G. All right. But you know what? Okay, wait. Okay, so G. 356G. Okay, so here's the key. We have a difference of logs. The difference of logs is log of a, not a difference, but a
Division.
yep, quotient. Yes. And it's a log base 5, right? Okay. Equals what, 4? In green, right? Good. All right. So that's the key. Okay, so let's proceed. Let's proceed. Oh, okay, now I'm gonna shrink this a bit because I want captions. All right, so we can do zigzag now, right? We do the zigzag, going to exponential form. 5 to the 5 to the 4th is that. All right, so we have 5 to the 4th equals x over x plus 1. 5 to the 4th, and students can use their calculators. It's 25 squared or 625. 625, right? Okay, 625. Ah, yes, this is a tricky algebra problem. Equals x over x plus 1. Okay, there's not much to do aside from multiply both sides by x plus 1. So you have 625 times the quantity, x plus 1 equals x. Okay, and I have a student who is offering what in here? Oh, okay, well, yeah, checking, you mean checking this work? Yeah, let's do that in a minute. All right. Okay, now let's do this. And then distribute. 625x plus 625 equals x. All right. Now we want to isolate the x terms on one side. Isolate x terms on one side. Minus x minus x. Oh, it's in the file. Okay, I gotta move over. All right. So when I move over here, it's going to be 624x equals, subtract the 625, right? Divide by 624. And by the way, you have to show this work, okay, even though okay, put braces, go home. What do you think? Put braces, go home? Don't go home. Check it. When you plug this into this, for example, no good. You're trying to take the log of a negative number. This does not check. Solution set is the empty set. There are no real solutions. Now, bear in mind, if I grade that G problem on the homework, if people put answer only, they're basically going to get no credit. I mean, you got to show me this, right? You got to show me that 10F solution. Right. Questions? I believe a student wanted me to check some work here on D. I'll Okay, let's check the student's work here. Oh yes, this works also. It works also. I think it's a bit longer, but it also does work. Very good, very good. You use the product rule. Yeah, because you can see how a lot of students start this off, but they often make mistakes, like they forget the product rule. Yeah, so very good. So you did it kind of the longer way, but the fact you did it correctly is very impressive. ln of e is 1, right? Yes, yes, yes. And then your final answer is a solution set. You want the braces. Yes, good, very good, excellent. Yes, it's good to try it different ways. So basically, you're avoiding factoring, but you ended up using a log property here. So, you know, to each their own. Yes. Oh, yeah, some great math here. Yeah, because a lot of students would get this wrong somewhere. All right. Okay, we're at 10:13. Night's young. Although you've worked hard. You've worked hard. Was there anything else? I think I got everything else in chat. Any questions?
Have we done 6F on the last section?
F. So I got the answer there. See F.
I ended up with a -3.
Ah, so there's a sign thing. Okay. I think I'm going to need a new paper. Okay, I'm going to get a new paper. I need a new whiteboard. I love my electronic whiteboards. I just started making them for Zoom, but they're so great.
Do you have one of the draw pad setups, or do you use a mouse?
Oh, see,
to write?
so on my MacBook, what I do is so basically, here's what I do. I go to text edit, right? I go to text edit, and I open a blank file. All right, I make it really big, and then I go to preview, and I take a screenshot of the white space. Okay, and then I can write on it. But the thing is, in order to make sure that you can keep manipulating things even after you save, you have to save in PDF format. That's why I made that comment in class, because it was saving in PNG format. But the problem is that if you do that, if you save and then reopen the file, then all the marks are frozen in there. It's like in concrete, and you can't change anything. So if you want to change, if you want the ability to change the marks you've put in there, then you have to save in PDF format. Yeah, but they're great. I mean, these are even better than the whiteboards in class. Anyway, I want the on-screen signs. Yeah. Yeah. See here, I have a bunch of PNGs, but then the stuff I have gets stuck. Yeah.
Do you do the writing with your mouse?
Yes, with my mouse, right? Because the trackpad, see, you notice that my videos weren't as clean because I was using my trackpad at first, but the control's not as good. I find that with the mouse, it's easier to write. So yeah, the mouse gives you better control. Also, one thing that helped a lot, see, in my early videos, I used very thin marks, and they might be harder to read. Although, if you have dense math, it might be better. But I think, the really thicker marks here, they're easier to read. They're more appealing. So you might want to thicken if you have like a Mac or whatever, you might want to thicken your mark. Yeah.
I feel like the school should buy you one of the drawing pad things with a real stylus.
Oh yeah, the stylus. But the thing is, now I'm not claiming that I'm a calligrapher here, but I think this is legible enough. I think we're okay.
Oh yeah, it is. It's just for like the ease of use for you. I feel bad that you have to write all this with a mouse.
You know, I've gotten used to it, and I don't like. I already have so many dongles on my MacBook now, right? With the Mac and the cooler. So no, I'm good. I'm good with the all-in-one. Yeah, I thought about it, but I think I'm good here. Yeah. I think it's so cool. I can do everything with with just a few pieces, right? Now again, my writing could be nicer, but it's not bad. It's okay. Let's see. Oh, I haven't graded anything yet. I'll email you your grades. Yeah, I know. I'll definitely grade something within, it better be a week. Jeez. All right. Anyway, let's get to the problem. Yeah. We're going to open a new file. Yeah. This has been such a great class, but I haven't had time to grade. That's the one thing. I can imagine the reviews. It was a great class, but he never gave our stuff back to us. And you laughed maniacally about it. No, I'll get stuff back. All right. Here we go. Here we go. Let's do G. Well, no. You said F, right? F.
Yeah.
Okay. Blue. All right. Blue. All right. Once again, quotient rule, right? That's the logical way of doing it. Quotient rule. All right. Log base 2. Don't forget the 2. A lot of students do that. Of the quotient, right? Which is, yeah, it looks like the algebra is going to be kind of heinous again. 10x plus 2, right? All over 7x minus 5 equals 1. So yeah, I think the algebra 1 is going to get people here actually. Yeah. Equals 1. All right. Not much to do. You can't do much with that. So you got to zigzag pretty much, right? 2 to the first is that. 2 to the first. I know you're supposed to line up the equals. Well, okay, I'll line up the equals. You're supposed to line up the equals. 2 to the first equals that thing. All right. That's 2. Okay. In fact, I'll do this. 2. I'm not going to do a separate step saying 2 to the first is 2 for crying out loud. Okay. And then just like before, we're going to multiply by the denominator, right, on both sides. So, but you might want to keep these restrictions. Well, you're going to have a problem with that 0 anyway. So, equals that. Okay. Oh, you said you got a sign flip somewhere. Yeah, you probably made some sort of mechanical error of some sort. Distribute 14x. But it's good to have a second pair of eyes to see where you did it. Minus 10. Although I wouldn't be surprised if I made the same mistake you did. 10x plus 2. My students are probably better at algebra 1 than I am. All right. And then what? You want to subtract? I'll do this in red actually. Well, maybe green. Okay. So you want to subtract 10x from both sides. (14x minus 10x is 4x. These are knocked out. Whoops. The zoom toolbar is in the way. Get out of the way, zoom toolbar. All right, I'll move my thing. There you go. Okay, let's see. Oh, okay, yeah. I was gonna strike. So these strike out. They add to 0. Okay, and we're gonna add 10 to both sides. Do that in purple. Of course, you don't have to do this, but many students like this, so I'm doing this for their benefit. You don't have to show this, but I'm doing this for student benefit. Okay. So we end up with 4x here. These die. Add to 0. Equals. These cancel. 2 plus 10 is 12. So I got positive 3.
Yeah.
Okay, and then that checks, right? Okay. Yeah. By the way, as long as you know the arguments are positive, you'll be good. Technically, there are other ways it could get messed up, and technically, you're supposed to go all the way with the check. You should do the check all the way, but I feel good. I mean, as long as it makes the arguments positive, I feel pretty good. And let's say that's the solution set. Do you see where you made the error?
I don't have my notebook in front of me right now.
Okay.
I'm at a different house right now.
Okay, but it's in the video, so you can track the signs. But I'm sure you knew what you're doing. I mean, a sign error, you know what you're doing. It's just that it's a basic human thing. All right. So, any questions about this? Any questions? Oh yes. Okay. So as we approach 1022, any questions? Any questions?
I think I'm good for tonight. Good night.
Oh, good night. Yes, thank you for staying.
Have a good week.
Yes. Questions? You're very welcome. Questions? Okay. I guess it's good night to all. All right. Good night, everyone. All right.